Hi to all, how are you? Welcome to srinivasphysicsclasses. Till now, if you not subscribe my channel, then subscribe, share and comment. Today's topic, class 12 4th chapter continuation. That is, today we are going to discuss Biotsavart law. This is very important for the board exam, and now I will start the Biotsavart law. What is the use of the Biotsavart law? The Biotsavart law is useful to find the magnetic induction or the magnetic field due to current carrying wire. For example, this is a current carrying wire. Then around the current carrying wire, magnetic field will be produces, that you know. According to Eirsted experiment, around the current carrying wire, magnetic field will be produces. That magnetic field strength can be measured by this law, that is Biot-Savart law. Then let us see what is Biot-Savart law. This is a current carrying wire, okay? And on the current carrying wire, we are taking the small element whose length is dl. Okay, now the length is dl. This dl is the small current element. Okay, small length, small part on the wire. Its length is dl. Dl is, we can take as a vector. Its direction is in the direction of the current. At point P, right? Okay, which is at a distance r from the current carrying wire or the current element. Okay, I want to find out the magnetic induction. Magnetic induction at point P I want to find out. That is, I am considering as dB. dB is equal to question mark. Then on what factors that depends according to Biot-Savart law? First point is that the magnetic induction at a point P due to current element is, first point, directly proportional to the current. Magnetic induction at this point directly proportional to the current. There is more current, then more field strength. Then, and second point is that directly proportional to the length of element. Look at here, we are taking the small element, then current field is also proportional to the length of element. And the next third point is that the magnetic field is directly proportional to the sin theta. What is theta at here? Theta is, this is the line joining the point P where we are finding the magnetic induction from the element. It is making some angle with the element, that is called as theta. Theta is angle between the dl and r. This is r and this is dl. The angle between the dl and r is the theta. Okay, theta is what at here? Theta is angle between dl and r, dl bar and r bar. We can take them as vectors. And the next point is that the fourth point, the magnetic induction. Here we are writing the magnetic induction inversely proportional to the square of distance. That means dB inversely proportional to square of distance. If distance is increases, if you go far away from the wire, the field will be decreases, right? Then dB inversely proportional to r square. Look at here, magnetic induction at a point P directly proportional to current, directly proportional to length of element, directly proportional to sin theta, inversely proportional to the square of distance of point P from the current element. What is point P? Point P is a point where we are finding the magnetic induction, right? And when we combine these equations, 1, 2, 3, 4, there are four equations are there. If you combine them, then we will get dB proportional to I, next dl, next sin theta, next by r square. When the proportionality is removed, we will get a constant at here, right? That constant is mu naught by 4 pi. Look at here, mu naught, this one. Okay, mu naught. Okay, mu naught by 4 pi into ideal sin theta by r square. Here the mu naught by 4 pi is the constant. In that 4 pi is the 22 by 7. What is mu naught? Mu naught is the permeability of free space. Permeability of free space. In electricity we discussed the epsilon naught, that is permittivity of free space. Nu naught is the permeability of free space. It is also have some fixed value, that is 4 pi into 10 to the power of minus 7 Henry per meter. And now this Biotsavart law, if you want to express in vector form, right? Here magnetic induction is a vector. It has some direction. If you want to express the magnetic induction, okay, Biotsavart law formula in vector form, you have to multiply this equation with r and divide with r. Okay, look at here, dB dB, nu naught by 4 pi, nu naught by 4 pi, I dl dl. Here I am multiplying with r, okay, r extra. Then again in downward also we can multiply with r, then it will become r square into r cube we will get. Here dl into r we are getting, right? When you cancel this r and r cube, again we will get ideal sin theta by r square, this equation. Okay, for this equation I am multiplying with r and dividing with r. Then we are getting the ideal r sin theta by r square. We have one formula, that is a bar cross b bar is equal to ab sin theta, right? A bar cross b bar is equal to ab sin theta. That formula we will use it here, and we will make the equation that dl into r sin theta we write as dl bar cross r bar. dl bar cross r bar means dl into r into sin theta, like that. Okay, right? And this is in vector form. This is a b sin theta. If a b sin theta is there, means that we can write as a bar cross b bar. Here dl r sin theta is there, that we write as dl bar cross r bar by r cube, r power 3. Okay, r power 3, right? And this is in vector form. Okay, and this is the previous question. And one more question, write vector form of Biotsavart law. This is the vector form. Okay, now you can take the screenshot and write the notes on this. This is very important topic. Biotsavart law is useful to find out the strength of the magnetic field due to current carrying wire. The strength of the magnetic field formula is this one, nu naught by 4 pi into ideal sin theta by r square. Okay, now let us continue. We will discuss the terms which are present in this equation. Okay, right? And now for that, what are the terms which are there in this? Okay, and now I will rub and then I will continue. Okay, let us continue our topic. That is, here we got the dB formula, this one, and now let us see what are the factors which are there in this. dB is what? dB is the magnetic induction due to current element, right? dB is the magnetic induction due to current element. Magnetic induction means magnetic field strength due to current element. What is the length of the current element? Current element, okay, whose length is dl. Okay, and now what is I we know current. I is the current. What is dl in that? dl is the length of element. Okay, length of element on wire. Element is what? Small part on the wire, that is the element. Its length is dl. dl is the length of the element. This is a current carrying wire, and due to this element at a distance r, I want to find out the magnetic induction, that I am considering dB. Then the dB formula we got this one. Why we are considering the dB? dB is the small magnetic induction due to small element. Right? If you want to find out the total magnetic induction, what you have to do? You have to do the integration, right? And now let us see here. Let us go for some more terms. What is r? R is already we know distance of point P, right? Distance of point P, where we are finding the distance of point P from element. From which element? Current element, right? Current element. Now Let us go for all the terms are completed. Magnetic induction due to total wire I want to find out. Okay, magnetic induction. Look at here, magnetic induction due to total current carrying wire I want to find out. Magnetic induction due to total current carrying wire, right? Already we know the current due to small element dl, we know the magnetic induction dB, but I want the magnetic induction due to total current carrying wire. Then how you will get that one? The total magnetic induction we will get is like this for the small element dB, next small element dB, next small element dB, like that for every element we have to find out the magnetic induction. We have to divide the total current carrying wire into different elements, and then for every element you have to find out the magnetic induction, that all magnetic inductions we have to add. That means summation of small magnetic inductions due to small elements gives the total magnetic induction. Instead of summation we write the integration symbol, integration dB. Okay, then the B is equal to integration dB. dB equation we write from equation 5, that you will get as nu naught by 4 pi into ideal sin theta by r square we write. Okay, and this is total magnetic induction. This you are writing from equation 5, right? Equation 5 from this equation. And then after that, in this some constants are there, means we can keep outside. Nu naught by 4 pi into, if any other constants are there, this already nu naught by 4 pi is a constant value, that already we know. If any other constant, then also we can write outside, but I am not writing anything outside. Okay, only nu naught by 4 pi I am writing outside. This is the formula to find out the total magnetic induction due to current carrying wire. This is equation 7. Okay, this is about Biotsavart law. Next we will discuss similarities and dissimilarities and differences between the Biotsavart law and Coulombs law, right? In Coulombs law we will find out by using Coulombs law we find out the electric field intensity due to charge. By electric field we can find out by Coulombs law, or the force we can find out by the Coulombs law, right? And here by using Biotsavart law we are finding the magnetic field. Then what are the dissimilarities and similarities that we are going to discuss? And before that I am going to rub the total board by pressing the pause button. Okay, now I am going to explain the comparison of Biotsavart law in magnetism and Coulombs law in electrostatics. Okay, we already know about the Coulombs law in electrostatics, right? According to Coulombs law, the force formula is what? 1 by 4 pi epsilon naught into q1 q2 by r square, right? Then according to Coulombs law we know formula for the force. According to Biotsavart law, just now we discussed. Look at here, electric field due to point charge by using Coulombs law. I am going to compare the Biotsavart law with Coulombs law. For that I am taking the equation of Coulombs law and equation of Biotsavart law. The equation of Coulombs law is that Coulombs law equation we know that force formula 1 by 4 pi epsilon naught into q naught by r square. This is the Coulombs law force formula, but I want the electric field formula from Coulombs law. F by q naught we have to do. Then we will get the electric field formula is 1 by 4 pi epsilon naught into q by r square. Based on Coulombs law we derived the formula for the electric field intensity, that is 1 by 4 pi epsilon naught q by r square. Okay, this is due to point charge. This is a q charge from r distance. Then electric field formula is, right, 1 by 4 pi epsilon naught q by r square. Now what about the magnetic field? For example, this is a current carrying wire, right, and this is a small element, its length is dl. From that at a distance r, right? The magnetic field dB according to Biotsavart law, right? Magnetic field formula is nu naught by 4 pi into ideal sin theta by r square. Here electric field inversely proportional to square of distance, magnetic field also inversely proportional to square of distance. Now this is based on, this equation is based on Coulombs law, this equation is based on Biotsavart law. We have to compare these two, and there are some similarities are there, some differences are there. Let us see similarities first. What similarities are there? Both fields inversely proportional to the square of distance from the source to point of observation. Here this is the point of observation, right, where we are finding the electric field. This is the point of observation where we are finding the magnetic field, and this is the source, it producing the electric field, and this is the current carrying wire, it is producing the magnetic field, right? And now here I am telling that the both are depends upon the distance, both are inversely proportional to square of distance. Okay, electric field inversely proportional to square of distance, magnetic field also inversely proportional to square of distance. Now one more similarity let us discuss. Both are long range fields, means up to long distance, then electric field will be there and magnetic field is there. Where electric field will become zero? If you take the distance as infinite, then electric field will become zero. That means to get the zero electric field we have to go to up to infinite. To get zero magnetic field, when you will get the magnetic field zero? If distance is infinite, then infinite, something by infinite will become zero, then the magnetic field is zero. In order to get the electric and magnetic field zero, we have to take the distance as infinite. That means up to infinite the electric field will be there, after infinite then it will be vanishes, it will become zero. And now this is the long range field, both are long range. And the next one is both obeys the principle of superposition, right? Principle of superposition is applicable for both fields, right? Here electric field due to only one charge. If many charges are there, we have to add, right? We have to add the electric fields due to all charges. Here similarly, here due to one element, here we are finding the magnetic field. If there are many elements on the wire, we are taking the small part is called as element, small part on the wire, and for every part there is some magnetic field is there. If you want to find out the total magnetic field, we have to add them. That means adding, okay, that is called as principle of superposition. Okay, and now the principle of superposition is applicable for the both fields. And the next, these are the similarities. There are three similarities are there, right? One is electric field and magnetic field. Both are inversely proportional to square of distance. And next one is both are long range and both obeys the principle of superposition. Let us go for the differences. What are the differences, right? And the difference is, the first difference is that magnetic field produced by what? Current carrying wire, that means current element. But the current element is a vector, right? Current element is a dl, is the length of the current element. It is a vector, its direction is from in the direction of current, right? That means magnetic field produced by the current element dl bar, right? Current element dl bar. But electrostatic field or electric field produced by the charge, but the charge is a scalar. That means magnetic field produced by the vector source and electric field produced by the scalar source, right? This is the difference. And next, second point is that magnetic field is always perpendicular to the plane containing dl and r, right? Generally we know, for example, we have C bar is equal to A bar cross B bar. For example, A bar is along the x axis, we write I cap. B bar is along the y axis, we write j cap. I cap cross j cap gives the k cap. That means C bar is along k cap. If A bar is along x axis, B bar is along y axis. If B bar is along y axis, what about C bar? C bar we got k cap. I cap cross j cap is k cap, that you learned in the 11th class, right? That means now when you do the cross product, we will get a vector. That vector is perpendicular to the plane containing the two vectors. Okay, right? For example, look here. This is a circular current carrying wire. On this small element I am taking, this is the dl, like this it is there. Okay, look at here, and this is like this. Okay, look this horizontal circle, right? And current element I am taking the dl like this, small element at here, and r is the, I want to find out the magnetic field at the center, right? What is its direction? Like this it will be there, And magnetic field direction I want to know. The magnetic field is always perpendicular to dl and r. Okay, here dB will be upward, will be there like this. Okay, based on the right hand rule also we can apply the magnetic field direction. Current carrying wire indicates the curled fingers, circle, and the field indicates upward. Magnetic field at the center is upward. That means magnetic field perpendicular to r and magnetic field perpendicular to dl also. Magnetic field is always perpendicular to the plane containing the dl and r. What about the electrostatic field? Is it perpendicular to this r or anything? No, it is not perpendicular to r. It is either away from the electric field or towards the electric field. If the q is positive, it is radially away. If the q is negative, it is radially towards, not perpendicular, right? Electric field is always radially away from the positive charge and towards the negative charge. Okay, here we are taking the positive charge. At point P, the electric field is away, will be there. If you take the negative charge, the electric field is towards negative charge, will be there. And the next third difference is that magnetic field depends upon the angle. Right, in this formula you see magnetic field depends upon the angle. This is the angle between the element and r. Angle theta is the angle between the dl and r. dl is the small element on the wire. R is the distance of point P where we are finding the magnetic induction from the element, and the angle between the dl and r is theta. Magnetic induction depends upon theta also, but here electric field does not depends upon the theta, right? Electric field does not depends upon the theta, right? Now that the theta formula is not there in that. Okay, that magnetic field depends upon the angle, but electric field does not depends upon the angle. These are the similarities and dissimilarities. Okay, and this is our topic. And next I will continue one topic, a small relation I will give, that is the relation between the nu naught and epsilon naught. You take the screenshot and write the notes. Take the screenshot. Completed? Okay. I am going to derive the relation between the nu naught and C and epsilon naught. What is epsilon naught? Permittivity of free space. What is mu naught? Permeability of free space. Okay. The property of medium which affects the force between two charges is the permittivity. The property of medium which affects the force, magnetic force, that is called as permeability. Let us see here. I am going to derive the relation between the mu naught, epsilon naught and C. Let us see the relation between the mu naught, epsilon naught and C. How we will derive the relation? What is mu naught in this? Mu naught is the permeability of free space. What is that? Permeability of free space. Permeability of free space. Epsilon naught is the permittivity of free space. What is it? Permittivity. Permittivity of free space. And C is the 3 into 10 to the power of 8 meter per second. That is the speed of light. Speed of light in free space. Okay, free space means vacuum. I want the relation between these three. How we can derive the relation? Let us find the nu naught epsilon naught value. Okay, mu naught epsilon naught value. That this I will divide with 4 pi and multiply with 4 pi. Okay, again we will get the nu naught epsilon naught. No problem, right? And look at here, mu naught value already we know, that is, but the nu naught value is how much? 4 pi into 10 to the power of -7 by 4 pi into, what is this? 4 pi epsilon naught value is what? 1 by 9 into 10 to the power of 9, right? Do you know this value? You write here, since one is nu naught is, we know 4 pi into 10 to the power of -7 Henry per meter, and one more is 1 by 4 pi epsilon naught value. Okay, 1 by 4 pi epsilon naught value. 1 by 4 pi epsilon naught value is 9 into 10 to the power of 9. Okay, based on this we will write this equation. Okay, this is the first point and second point. Nu naught value we are writing here, and 4 pi epsilon naught value also we are writing. 1 by 4 pi epsilon naught value 9 into 10 power 9. 4 pi epsilon naught value, what happens? 4 pi epsilon naught value, you can write the reciprocal. 4 pi epsilon naught is equal to 1 by 9 into 10 power 9, that we are writing here. We can simplify this, and finally we are getting the nu naught and epsilon naught value as 10 power minus 7 by 9 into 10 to the power of 9. This we will take 10 power minus 7 to denominator, then we will get nu naught epsilon naught is equal to 1 by 9 into 10 to the power of 9 plus 7, we will get 16, right? And this we can write as 1 by 16 we write as 3 square. Okay, 3 square, 10 power 16 we write as 3 into 10 to the power of 8 whole square we write. Okay, what is 3 in 10 power 8? That we write as C. Then mu naught epsilon naught we will get as 1 by C square, right? From this we will get the C square is equal to 1 by nu naught epsilon naught. Then C is equal to we will get as 1 by root nu naught epsilon naught. Okay, this is the relation between the mu naught epsilon naught and C. C is the speed of light. The speed of light in terms of permeability of free space and permittivity of free space. Nu naught is the permeability, epsilon naught is the permittivity. And let us see, here we are finding the magnetic induction by using Biotsavart law. But how to find out the direction of the magnetic field? The direction of the magnetic field we can find out by using Biotsavart law. Let us see that right hand thumb rule is used to find out the direction of the magnetic field. What we have to use? Right hand thumb rule. Okay, let us discuss about that right hand thumb rule. Now, how we can find out the magnetic induction? Let us see right hand thumb rule. Already we discussed in the previous class. Right hand thumb rule. The right hand thumb rule is that this is used to what is the purpose of this? This is used to find the direction of magnetic field, right? Direction of magnetic field due to current carrying wire. How to find out it? Already we discussed it, right? Let us see. Okay, when the thumb shows the, if thumb shows the current, then curled fingers shows the direction of magnetic field. If this is the first point, okay, right? The first point is that if thumb shows the current, then curled finger shows the field. If curled fingers shows the current, then thumb indicates the magnetic field. Okay, this is the second one. Let us draw some diagrams related to this. Here we are taking the current carrying wire right upward. The current is in upward direction. This current carrying wire is held in our right hand in such a way that I want to find out the direction of the magnetic field. Okay, right. At that moment, now how to find out the direction of the magnetic field at here? Look at here. This is considered as a tip. Tip of my pen is upward. Okay, tip of pen is upward. That means current is upward. We can consider. Then we have to hold the current carrying wire in such a way that the thumb shows the direction of current. Okay, thumb, this one shows the direction of the current. Okay, upward, and curled fingers like this will be there, right? This there like this from this side entering, right? This side entering and this side coming outward. Okay, the field will be like this there, right? The field is like this there. Okay, and here it is leaving, here it is entering. Okay, why this side entering and this side leaving? Okay, the leaving field here we write as the leaving magnetic induction, we write as dot. Here dot B, here we write as cross. Okay, cross B. Cross indicates inward magnetic field. Inward magnetic field. Okay, how I am telling that is inward? This side entering and this side coming outward. Look at this is a pen, current is upward, thumb upward, and this side entering, left, this side entering, and this side coming outward, fingers, curled fingers. That's why this side outward magnetic field, this side inward magnetic field. Okay, this side inward magnetic field, this side outward magnetic field. This indicates outward magnetic field. Outward magnetic field. Okay, right. In the same diagram, if it will be like this there, right? If the current is in downward direction, if the current is in downward direction, look at here, the current goes downward. At that moment, what is the direction of the magnetic field lines? Okay, how the magnetic field will be there? The thumb shows the direction downward, current is downward, thumb indicates the current downward, and curled fingers indicates the magnetic field. Curled fingers indicates the magnetic field. Then for example, here we are taking the tip of the pen is downward, the current is downward. We have to fold this in our right hand in such a way that the thumb should show the direction of the current downward. Okay, and what about the curled fingers? This side entering, this side entering we write as cross, and after that this side leaving, coming outward, they can write as dot. Okay, here we write as like this, and that is like this we have to write. This side leaving and this side entering. Okay, and now the field we can write like this. This is leaving, that's why here dot field, and this side entering, that's why cross field, right? Here dot indicates leaving and the cross indicates the field entering. Okay, and like this, and it will be in circular form. Then like this circle will be there, right? Okay, and if we draw the diagram like this, and in the shape in the form of circle like this, the current is in upward direction. If you take a plane of paper like this, okay, we will take a paper like this, and then at that moment, then the field lines, how it will be there? The field lines will be like this. It will be there in the circle shape. Okay, and what about the direction of the field lines? Field, okay, current is upward, means field lines are anti-clockwise, right? This side entering and this side leaving, this side entering and this side leaving. And if you want the field direction at any point, then we will get tangent we have to draw, then along the direction the field will be there, right? The field is not upward in the plane, it will be there, right? Like this. Okay, and this is magnetic field direction by using right hand thumb rule. Okay, here in these two cases, the current indicates the thumb. Okay, in above cases, in above figures, right? Tell me what current shows. Current is the thumb, right? And curled fingers are the field, right? Field is the curled fingers. Now let us see. Current may be indicated by the, if you will take the circular current carrying wire. Okay, I am taking the circular current carrying wire. Then what about the magnetic field? How to find out the magnetic field direction due to current carrying wire? Circular current carrying wire. Okay, right, let us see. This is the case. For example, this is the first example here, this is the second example, and now I am giving the third example. The fourth I will tell, that is field due to circular current carrying wire, right? Field due to circular current loop. Okay, look at here, circular current loop I am taking. This is a current carrying loop. It is there like this. Okay, circular current carrying loop I am taking. How the direction of the magnetic field will be there? Okay, how to find out the magnetic field direction? This is a circular loop. Okay, okay, look at here, the current flows like this. If there is a current carrying wire, the current flows like this in anti-clockwise. This is also one current carrying wire, right? The current flows in clockwise, right? Circular current loop, circular current loops. Okay, what about the field direction in this case? In this case, in above case, what we have to do if you want to know the direction, then here the I curled fingers, right? I curled fingers should be there. Okay, curled fingers, and B is the magnetic, and B shows the thumb. Okay, look at here, how to write that. Now it was very simple. Okay, and you see this and try to apply the thumb rule. The thumb rule we can apply like this. Look at here, this is the thumb rule, right? Curled fingers and thumb. Right hand you have to use. You have to use the right hand, right? This is the winner. Okay, now let us see. Here the current is in anti-clockwise. What about the field direction? Field is outward like this. Current, curled fingers indicates the current. Current is going like this. Okay, fingers are showing this side, like this, right? The fingers, curled fingers are in anti-clockwise. Then what about the field at the center? Field at the center is outward. It is coming out from the plane of paper. Then that is outward we indicate with the dot, right? This is the dot. Okay, field is outward. And what about at this location? Now see here, current is in current carrying wire is in circle shape. Then in this, okay, we cannot indicate the current with the thumb. Why? Current is not in one direction. If one direction straight wire, there means current is indicated with the thumb. But the circular wire, the curled fingers indicates the current, right? The current is clockwise this side, and thumb is entering into the board, right? Entering into the board. Look at here. Okay, curled fingers. This side is there, and thumb is entering. then entering field is indicated with the cross. This is the cross field, right? Cross field. Okay, inward magnetic field we can write as cross, outward magnetic field is dot. Inward means what? Inward is the perpendicular to the board. Inward means field is inward, perpendicular to the board. Okay, and enters into the board. Okay, and sometimes this is, okay, here you see this cross I, like this it will be there. This also we say that if after the cross if I is there, it indicates inward current. Inward current. Note, this is the note I will write. I will give in the note. Right? Note. Okay, this will indicate the inward current. Inward current means current entering into the plane of paper and it is perpendicular to plane. Okay, right, perpendicular to plane of paper. Now what about the dot I? Okay, right, this is outward current. Okay, if like this there, this is what? Inward magnetic field. And like this there, what is this? Outward magnetic field. This is inward magnetic field. Okay, this is the outward current. Outward current means current perpendicular to plane and outward. Okay, right. And this is the, for example, current carrying wire is like this there. How to draw this in the figure? Current carrying wire is like this there. It is perpendicular to the board. Then that such type of current carrying wire we can draw with dot. Okay, or the cross. Okay, this is the current carrying wire. Current is entering. Okay, means we write cross I. Wire is perpendicular to plane, like this there, like sketch. This one how we draw in the diagram? Just we write cross I. Right? This one is dot I. Dot I indicates the current outward. Okay, right, like this we can indicate. Thank you for watching my lectures. Subscribe my channel. If you have any doubt, you can contact me in WhatsApp. Thank you.